All right, students, it is Thursday. We are almost done with this week. We are trucking along. I've been seeing a lot of people do a lot of good work. I like that. It's showing your maturity over the course of the year. A lot of people are almost done with the student workbook in a few classes. So I like that. If you're not one of those students, make sure you are being on your game today and getting as much done as possible. As I told you last night or yesterday, you should have done work yesterday and last night to be able to be up through page 13 today. If you are up through and done with page 13, you are on top of your game. If you're not, you need to step it up. We're moving quite quickly. All right, so let's just jump right in here. Thursday, the do now says a bar of soap floats in a bathtub. The buoyant force acting on the soap is equal to, here, okay, the buoyant force you should know from Archimedes Principle, which we'll skip down here because this will help us come back and answer the do now question. You should know this already. It's from the book. Archimedes Principle tells us that the buoyant force that's acting on an object is equal to the weight of the fluid, okay, that is displaced by the object. Okay, so when you put one object inside a fluid, it moves some of that fluid out of the way. And if you can measure the weight of that fluid, okay, that weight would be equal to the buoyant force. So here, when we say a bar of soap floats in the bathtub, the buoyant force acting on the soap, well, then it must be equal to, the answer should be D, the weight of the water that is displaced by the soap. And we know this because of Archimedes' principle here. The next do now question, or the do next question, says, how does the force of gravity compare to the buoyant force acting on a floating object? Okay, so if the object is floating, that means it's not moving up and it's not moving down. You don't have to draw this picture per se, but let's say I have an object and it's floating. That means that the forces are balanced, okay? The force going down is gravity. We know that. And then we also know now that the force that's acting up is the buoyant force. Okay, and so if it's floating, then the buoyant force must be equal to gravity, because they balance each other out. So when we say how does the force of gravity compare to the buoyant force acting on an object, okay, we could say that these forces are equal. Okay, or you could say or balanced. All right. Now, I said you should be done with up to page 13. Okay, so we did all the active reading note or the essential reading yesterday. So I want to go over these active reading. I'm going to go over page 12, 13, and actually on page 14. So if you didn't get this done yet, you need to quickly pay attention. Once again, please don't just copy. If you are copying this, you need to make sure you go back and read it. Okay, in an ideal situation, you would have done this already. Also, as you know, I'm going to go quickly. If you don't get it when I go through it right now, it's because you haven't gotten it done. If you've gotten it done, you simply be just checking your work. Also, you can check and see which page is on. At the very least, get this down, so if I go too fast for you, you can go back and find the information for yourself. All right, so it says here, classify the two types of liquids and give an example of each. All right, we learned yesterday that fluids can be either liquids or they can be gases. Okay, and liquids here, you could put a lot of different things. Okay, you only have to put one example. You could put, okay, water, milk, juice, alcohol, a lot of different things. Okay, you could put anything here. I'm just going to put etc. because it could be a lot of things. Gases. Okay, there's gases. There's oxygen. Okay, there's the air, which is a mixture of gases. There's nitrogen. There's all these gases out there. Helium. There's many different types of gases. Okay, so you just have to put one example there. So here, it says summarize the effects of force and area on pressure by completing the diagram. Okay, so right here, if you think about it as a math equation, okay, pressure is equal to the force over the area, which we talked about yesterday. So how can we increase this pressure? If this was a fraction, okay, if the numerator of the fraction gets bigger, this number gets bigger. So in this F stands for the force. So if we increase, the pressure can increase by if the force increases. So we're just going to put the force applied. If the force applied increases. Also, remember, in a fraction, the bigger the denominator gets, the smaller the overall fraction. So for example, we have 1/2 and we have 1/3. Okay, we see that here 3 is larger than 2. Okay, but if you look at the whole fraction, 1/3 is smaller than 1/2. So as the numerator or as the denominator increases, the overall value of the number goes down. So if we want the pressure to increase, we need this number to get smaller. So the smaller this number gets, see how 2 is smaller than 3, but that means 1/2 is bigger than 1/3. So if the area decreases or gets smaller, then the pressure will go up and the pressure will increase. So we can say by decreasing the area. And this makes sense if you think about it. We talked about it yesterday. Okay, if you stand in one spot on a bed, the pressure will be greater because all of your force is applied to a small area. Okay, but if you spread your feet out, okay, you're increasing your area, and then the bed doesn't indent as much, and so you're decreasing the pressure. Okay, so the larger the area, okay, the smaller the pressure. But that also means the smaller the area, the larger the pressure. So this leads right into this question right here. It says, sequence the diagrams to show how pressure is related to surface area. Okay, number the diagrams. That's 1 that has the least pressure and 3 that has the most pressure. Okay, so with all of these, you can see are applying a force of 5 newtons. Okay, so but which of these is going to have the most pressure applied? Okay, well, if we look up here, we know that pressure increases as you decrease the area. So even though they're all 5 newtons, we see here, this is like if you were standing on a bed with your feet together. You see how the surface area of the bottom of this box is very small. It's all in a small area. So therefore, this is going to be the one that applies the most pressure. And the one that with the largest surface area in contact with this bottom here is going to be this one. So it's the most spread out. Okay, so you're spreading out the force that's being applied. So this is going to be the least pressure applied, and so that means this one must be in the middle. Okay. Make sure you go back and do your summary so you can kind of summarize what we've learned on this page. All right, let's go over to page 13. All right, you can find this information on page 142. All right, and so it says complete the equation for calculating pressure, include the units for each measurement, and then write in the symbols. Okay, so pressure, okay, there's different units. You know how for force we use newtons, okay, which actually is part, you know that pressure is equal to force over area. Okay, we know that. And then we know that we measure force in newtons. That's our units. Okay, area, it tells you here, is measured in meters squared. If you want to abbreviate, that'd be meters squared like that. And if you look in the book, the units for pressure are called pascals. Okay, that's named after a scientist whose name was Louis Pascal, who did some experiments with pressure. All right, so here, this information can be found on page 143. It says, analyze how the pressure exerted by a fluid changes with height and depth. Okay, now, when we say the height of a column, as the height of a column increases, so here, let me show you in the book, because I said this is on page 143. Notice here, okay, in these graduated cylinders, each one of these graduated cylinders has the same volume of liquid. They each have 100 milliliters of liquid in them. However, the pressure that's exerted by one of these is more than the other one. And this is similar to the box that we just looked at. Okay, see how this column here is taller? All right, and so because it's taller, it's exerting its force over a smaller area here at the bottom. Okay, and so remember, as the area increases, like again, like standing with your feet close together, okay, you exert more pressure. So it's because the surface area is smaller here, it's going to exert more pressure even though it's the same amount of fluid. Okay, here, okay, this one is going to, actually this one would be more, because if you look closely, this one has 300 milliliters of water and this one only has 100. So even though, see, the height is the same, okay, but because there's more volume here, it's going to have more force. So that would be the case in this one. So that's going to help us answer this question. It says, as the height of a fluid increases, okay, that's going to mean okay, the pressure on the surface increases. Okay, because the taller it gets, the more volume it gets, it's going to exert more pressure. And now it says as the depth below the surface of a fluid increases, what happens? So this is just like you're in a swimming pool. If you go below the surface, the deeper you go, the more pressure you feel. Okay, so this is whether you're in liquid or in air or any fluid. Okay, so as you go deeper in the fluid, the pressure increases. All right, let's look at this next example. It says model the effect of pressure on a fluid at different levels. Indicate the force with which milk will squirt out of holes punched in the side of a marked carton. So let's say this carton was full, okay, and let's say we put a hole here, and a hole here, okay. Which one is the milk gonna come out of faster? Okay, if you're thinking that pressure increases with depth, so this is deeper in the milk, if you example, so there's more pressure here. So here, okay, the milk will come out stronger than it would come out here, and then it wouldn't come out as strong here, because as you go down, okay, the pressure increases. So this hole right here is going to have the whole weight of the milk on it, so it's going to come out with more force. Okay, so that's kind of what that's showing you there. Same with here, okay, higher elevation. Elevation means like the height above the earth. Okay, so like airplanes fly at a high elevation, and if you're close to the ocean, you're at a low elevation. You're kind of like at sea level. Okay, so the higher you go up, okay, remember there's also like the air, like think of the air, let's see, I'm going to draw like pretend like this is the earth. Okay, and then here we have a person. Okay, remember the air is also a fluid. Okay, and so the higher the, like, and let's pretend like there's like a little column here, just like we do the graduated cylinders, except we're talking about air. If you go to the top of a mountain or you increase your elevation, there's less fluid above you. Okay, so you're going to have a lower air pressure. Okay, that's what atmospheric pressure is. Atmospheric pressure is the air pressure. Okay, but like here, when you're on Earth, it's like you're deep in the air, like kind of being deep in the swimming pool. So there's more air above you. Okay, so you're gonna have a higher air pressure here. So this tells us once again, okay, the higher the elevation, okay, the lower the atmospheric pressure. Okay, and then once you go over this again, make sure you do your summary. Now let's go over here to page 14 quickly. Okay. Here, this information can be found on page 146 where it talks about this, and this is kind of confusing for kids, and like I want to make sure I go over this quickly. Okay, so you'll notice this same kind of example on page 146 here where we have a picture of Nate here. Okay, for real, that looks like him, don't it? Okay, yeah, all right, you know it. All right, settle down, stop laughing. Okay, especially if you're in fourth period. All right, I'm joking, you know I love my students. All right, so it says model the buoyant force on an object. Okay, draw a fish underwater, which we've done here. Okay, I didn't even draw the water. Okay, yeah, you like my sound effects. Okay, so it says use arrow to show the forces acting on the fish. Okay, so we know that gravity always acts down, so there's a force going down here. And then in a fluid, there's pressure being exerted in all directions with perpendicular to the surface. So here, okay, there'll be a force here. Okay, and a force here. Okay, as we show in the picture. Okay, and then there's also the buoyant force, which acts upwards. All right. Now, remember, the deeper you go in a fluid, okay, the higher the pressure. So, like, look, you said, you know, notice how the bottom of the fish is going to have a slightly greater pressure acting on it than this up here. Okay, and it wants us to explain why the net force is upwards. Okay, so first of all, okay, these two right here going left and right, these would be the horizontal forces. Okay, so the horizontal forces cancel out, and the pressure is greater at the bottom of the fish also the buoyant force acts upwards. Also, the buoyant force acts upwards, resulting in an upward net force. So the net force is going to be up the body water. So the horizontal forces cancel out, and the pressure is greater at the bottom of the fish. Also, the buoyant force acts upwards. All of this combines to give you a net force that is up. Then it says put Archimedes Principle in your own words. Now remember that Archimedes Principle tells us that the buoyant force is equal to the weight of the displaced fluid. Okay, so we can just say, remember, displaced means to move out of the way. Okay, so we can say that the buoyant force is equal to the weight of the fluid that is moved out of the way by the object. The buoyant force is equal to the weight of the fluid that is moved out of the way by the object. Here, it says, complete the diagram to show what determines the weight of the fluid displaced by the object. Okay, the weight of the fluid is going to depend on two things. It's going to depend on, first of all, the density of the fluid. And it's going to depend on the volume or the amount of the fluid that you have. Okay, if it's more dense, okay, that's going to make it have a heavier weight. And if there's more of it or less of it, that's going to, the weight's going to also depend on that. So the density of the fluid and the volume of the fluid. All right. So actually, I'm going to go ahead and really quickly go over the reading essentials, because after I finish this, then you're going to be able to have, you're going to have everything you need to be able to complete the rest of the workbook, and I want to make sure you do that. So I'm going to go ahead and talk about sinking and floating on page 17. You need to go through and read this. You need to do the foldable. Okay, we'll make this one the gold foldable. Okay, so you make use the gold foldable, and then this one from way back over here, okay, we'll make this one the yellow foldable. This is on page 9. Okay, so this will be the yellow foldable. All right, so let's look at this. I'm gonna go over this quick, okay, so because give you the most time to get the work done. Okay, so just basically, how can you determine if an object is sinking or floating or not? So basically, if the object or the substance is, one substance is less dense than another one, it will float on another. So let's say you can even have two liquids floating on each other. Okay, you can have the less dense liquid will be up here, more dense will be down here. I'll show you this tomorrow. You can actually take two liquids and layer them on top of each other without them moving. Okay, and also let's say you have, okay, like, you know, a rock. Rocks sink because they usually have more density than water. Okay, but if you have an object that is less dense, okay, this is more dense, okay, you sink. So if you're more dense, you sink. Okay, less dense, okay, draw here, okay, you float. I mean, that's the basic outline here, because here we have, this is a rough drawing, but object floating on water, okay, because it's less dense than the water. Here we have an object that's more dense, and it doesn't even have to be just liquid. Okay, I mean, it could be, I mean, it can be, it doesn't have to be water, because all substances have densities. Okay, it says circle the object in the figure that is less dense. Explain how you know. Okay, we know here in this picture, okay, the boat is less dense. We can circle that, and we know because it's floating. Okay, the boat is floating because it's overall, that's terrible, overall density is less than the water. Okay. Now then it talks about hydrometers. We don't have hydrometers in the classroom, but hydrometers are this little liquid, this little device. It bobs up and down in the water. You can read around it here, and it measures the density of the fluid. But it does that by displacing a volume of fluid, okay, that's equal to its weight, okay. And that tells you right here. Okay, no, it's not time for you to go. That's the bell for my first period class, okay. And you can just simply write that right here, okay. It displaces a volume of fluid that's equal to its weight, and that's how it works. Okay, the higher the hydrometer floats up in the water, the least dense the liquid. Okay, and then the deeper it goes, the more dense. All right, over here on page 19. Okay, we already know that the density of water. Here, you should know this. You need to memorize this. Density of water is 1 gram per milliliter. We know that. Okay. Now, anything that has a density greater than 1 will sink. Anything that has a density less than 1 will float. And here it says, even if you have an unknown density, and if it tells you that the density of that is twice of water, well, 1 times 2 is 2 grams per centimeter. Okay. So over here, this question is asking you to calculate the density of an unknown liquid that is 4 times the density of water. Well, if density is 1 gram per milliliter, 4 times that will be 4. So the density will be 4 grams per milliliter. So pretty simple. And then it says, why does a helium balloon float? Okay, remember, the air is also a fluid. And so the density, if the less dense object will float in another one. So helium balloons, which you've seen at birthday parties, quinceañeras, and all this stuff, okay, they float because their overall density is less than the density of the air. Okay, their overall density is less than the density of the air. Sorry, you can probably hear people outside yelling. Okay, and then if you flip over here, okay, it says what causes hot air balloons to rise or sink. In a hot air balloon, you know, they take the little fire and they ignite the fire. Then fire heats up the air. If the air is heating up inside, okay, it causes the particles to spread out more, so they become less dense. And if the overall density of the balloon becomes less dense, the balloon will go up. When they turn the fire off, okay, the particles slow down and they become more dense over here and go up. If the particles cool down, they become less dense, okay, and then the balloon sinks. So what causes the balloon to rise and to sink? Okay, by changing the density of the air particles in the balloon. Okay, and then if you can make them less than the air around you, it goes up. If you make it more, it goes down. All right, get to work. Finish the whole workbook. Okay, you can do it.